All right, so let's go to the notes page. What I give you here, you're gonna, you want to know like where it is in your book because it's going to be useful in certain proofs. Okay, so you guys probably have heard about properties of equality, right? Like if you add the same thing to both sides of the equation or subtract from both sides, isn't that a property of equality? Doing the same thing on both sides at equal sign, right? So we have certain properties of equality, or abbreviated like this, POE. Okay? So let's say I have an equation I'm working on, right? So let's say I have something like 3x minus 4 equals 16. Okay? So you know how to solve this, right? What's the first thing you do to solve this equation? So if we add 4 to, well, specifically not just adding it to 16, but what?
To 4 as well.
To both sides of the equation, right? And so we end up with 3x equals 20, right? Okay? So what we did here, we added something to both sides. This is called the addition property of equality, okay? Or the addition, POE. Okay? Makes sense, right? You know what property of equality is, and this is addition. So then what do we do now? Okay. So now, divide both sides by 3, right? So we get x equals what? What are they?
6.6.
Yeah, 6. Well, yeah, 6 2/3, right? Whatever it is. Okay. So what we did right here, what would this be called? Division property of equality. Yeah. Okay. So if this is a property of equality that we did, it's valid, and we just justified dividing both sides by 3 because we know it's an equality, right? Or maybe I have something like this. Maybe I have an equation that has x over 4 plus 5 equals 8. Of course, here we would subtract 5 from both sides, yeah?
Yep.
And like I said, at this stage in your you don't always have to show this step when we're really doing it, but I want to show, right?
Maybe subtract.
'Cause like-
until end it.
Yes, because if I just wrote what the next line is after subtracting 5, you all would know what happened, right? At this level, okay? So we can take some make it show all your work. We have some shortcuts built in because we're taking steps up. So this would be the subtraction property of equality. Oops, let me just actually write that. Why does it decide like we're? All right. So that leaves us then with just x over 4
We multiply by 4.
equals 3. So here, right, we would multiply both sides by, yeah, how about 4? Right? So what would we call this?
Multiplication.
Multiplication. Multiplication. I'm not that smart. I can't spell. I can't spell too good. Goodly. Okay? And of course, the 4's cancel, you end up with x equals 12, right? Okay? So those are properties of equality. These are all possible proof reasons that you could use depending on what you have to do in your proof to get where you want to go, okay? So now we have some more tools in our belt to justify statements that we might need to make later on. And you'll see a few. Okay? All right, let's go back. There's the beginning. So we know, right, we learned that the angles of a triangle add up to what? Okay, 180 degrees. Now what else also adds to 180 degrees? What kind of angle? There's a straight angle, right? A straight line. And remember, angles of a straight angle add to 180. They're supplementary, right? So triangles angles add to 180. and angles of a straight line or a straight angle add to 180. So this is an informal proof, right? This isn't going to be statements and reasons, okay? So what we're going to do is we're going to use rigid transformations to prove informally that the angles of a triangle add to 180, okay? So I'm not going to hand out paper triangles. I don't do arts and crafts here. So I think you could all imagine in your hand holding a paper triangle on your desk, right? Okay? So what we're going to do with this paper triangle, we know that the angles add to 180, yes? Okay? You're going to tear off corners B and C. See how they look like they're kind of torn off, right? And you're going to translate them, all right? We're going to do a translation of just these corners we tear off, okay? And what do you know about translations? Right, so we got C got torn off and B got torn off, right? And B gets moved here, translate it there, and then translate C to there. Everybody good? Put them up there with A. So now we have those, what were all angles in the triangle, angle A, B, and C. What do they form up there? A straight line. And those are now angles of a straight line, right? So what do they add to?
180.
180. We see the connection there? So we took a triangle and was able to make it into a straight line to prove that the angles have to add to 180 degrees, okay? So angles, and this is another proof reason that might be available, angles of a straight angle add to 180. And we've just pulled those angles from a triangle, right? So we've used all the angles in a triangle, haven't we? Isn't this all of them up here now? Translated them, rigid, okay? So we connected a triangle to a straight line and also connected it to a rigid transformation, didn't we? Okay, we got all kinds of connections going on in this class, don't we? Okay, so now let's look at a classic proof down here. The kind we've been doing, statements and reasons. So what are we given here? Triangle ABC, not much given, right? And what do they want us to prove?
Angle 1 is plus the measurement of angle 2 plus the angle 3.
In other words, they want us to prove that the angles of a triangle add to 180, right? Okay? Now, one thing you can do on a proof, and you're free to do this. Does anybody see what they've done to help here? What was the first thing they did here? They drew an auxiliary line. We got that? You can construct an auxiliary line in any diagram that you like, right? And claim that, and what do they claim about this auxiliary line?
That is parallel to segment AC.
So now, so after the given, so they're stating that they have AC parallel to this BD that they drew in there, right? And the reason they can justify this statement is because you can always just draw an auxiliary, construct an auxiliary line in there. Everybody got that? So now we have two parallel lines, yes? Do you know anything about parallel lines with transversals?
They have to add to 180.
Nope.
No,
Nope.
the alternate interior
Angles of a straight.
angles are congruent.
And other things, right? You know, alternate interior. And by the way, I forgot, yes, I have that stuff up here. You just have to know which angle pairs they are, right, that you're looking at. Okay. So, here's what they do. Do you see angles, just like the triangle with the paper one we tore off, do you see angles 4 and 2 and 5? What do they add to? Okay, so they stated that. Angle 4 plus measure of angle 2 plus angle 5 equals 180. What's the reason there?
Angles of a straight angle add to 180.
So that was what I gave you up there. So it could be a reason and a proof. So there we go, right? So we established that these three add to 180, right? Okay. Now they say that angle 4 plus angle 1 or equals angle 1, right? Why does the measure of angle 4 equal measure of angle 1? Because why? Those are alternate interior angles because we made parallel lines, right? You with me? And now they also say the same thing, angle 5, the other transversal, and 3 have equal measures, right? Same reason. You got parallel lines, those are alternate interior angles. Everybody with me? Okay? So we know these 3 add to 180, right here. And we know these 2 and these 2 are congruent, right? Or the same. Now, what can you do, like in your algebra, right? When you have something that's equal to something else, can you not substitute one for the other? Can you substitute them in?
Yeah.
Okay. So look at this right here. So you see this statement 3 here? 4 plus 2 plus 5 equals 180, right? But down here, what did we say that 4 was equal to? So you see angle 4 here? Can I just substitute it with angle 1 since they're equal? And we justified why they are, right? Everybody got that? So if 4 equals 1, I can take this equation right here, right? I'm rewriting it down here, okay? I can replace 4 with 1. So instead of 4, look at it. Measure of angle 1. We got angle 2. Now, measure of angle 5. What can we replace it with? Right? So 4 can be replaced with that. Since they're equal, right? 5 equals 3. So 5 here gets replaced with 3. And what does this say now? What we wanted to prove, isn't it? And what was the reason that we could do this? Yeah, I probably should say substitution POE. I guess it doesn't matter. So does that kind of make sense to you? So we've just proven, and this is stuff, like I said, it has to be done. I mean, the ancient Greeks did this thousands of years ago, right? And the only way that you could move on, safely knowing that the angles of a triangle at the 180 was that it was proven somewhere, somehow. Otherwise, you couldn't accept it. But you can see it's proven, and now you can accept it, right? In math, we don't just take someone's word for it. We have to know that it was proven. Does that make sense? That's how that works. All right, what do I got next? Yes.
You said Egyptians or something? They used this method?
Greeks, Egyptians, yes.
So if they didn't know the measurements, how did they?
So that's interesting. They'll say like the Greeks, they knew about specific right triangles, right? And I'm sure they, in their language, they had some other name for it, right? But they knew about right triangles. I'm going to just pause this. So another transformational proof, an informal kind of proof, right? So what I want you all to do right now is take a look at this. We're given triangle ABC. So another way to think about proving that the angles add up to 180. So everyone right now, read this over, okay? Look at the diagram, look at the given, and then read through this and see if you can work out by transformations how they prove that those angles add to 180. Okay, I'm going to give you all a minute to read that over. They translated this triangle up, right? And so what happens then? So take side AC now, and the image side A prime C prime. What can you say about them after that translation? They're parallel, right? Okay. So translations preserve parallelism. Okay? So then they say we got these parallel sides, right? So we have angle 1, 2, and 3 here, right? Now look at here. After we translate it, do we see these 3 angles right here? What do they form? They form a line. What do they add up to?
180.
180 degrees, right? So 2 and 3 and 1 add 180 degrees. With me? Let me ask you this, though. So we have parallel lines in a transversal, right? Why is this angle 3 here? How do we know that that's equal to angle 3 here? If those lines are parallel. Yeah, okay, so I see what you're getting at. You're doing like after translation, corresponding parts are congruent. But these aren't really corresponding parts. This is not that angle after you translate. I mean, this one is. But what? The lines are parallel, and those are alternate interior angles, aren't they? Right? These guys are alternate interior angles, so they're equal, are they not? Okay. And 2 stays where it is, right? But look at here, 1. Isn't that corresponding with that angle there? Right? And so they're congruent. And so if these three are these three, and we know that these three here add to 180, what can you say about these three right here? They also add to 180 because they're equal, right? So it's like an informal way of looking at the substitution we did in that last one, right? There's all kinds of different ways to prove things. We're generally going to focus more on formal to count proofs, but it's always good to see, see it from a different angle, I think, okay? All right, now that we've proven that they add to 180, right, now we can officially use that fact in some calculations, because we've proven it. So now we know it. So here's an example. So we got this triangle, determine the measure of angle A. There's two of the angles. We've done this before. How do you find that missing angle? Subtract the two you're given from what the total is, 180, and you get 61 degrees. Simple as that, okay? Everybody with me on that? All right. So take a minute right now. I don't want you all to do A, B, C, and D here. Okay? A, B, C, and D. Find the missing angles.
D is different.
A little bit. D is a little bit different.
Divide it.
So by the way, in D here, when you get to D, let me just show you. That's their little angle congruent marks. That makes that an isosceles triangle, by the way, doesn't it? So I would, in D, I would take one of these and call it X, and if they're both equal, call that one X too, right? So then you can write an equation for that and solve it. I'd like to see the equation for that.
When they teach you on the next page, it's just 180 minus 50 equals 130 and divided by 2 equals.
Yeah, right. That's one way. And then we'll do it like algebraically, and you'll see that you're really doing the same thing.
But isn't that easier?
You gotta know your way around both, right? You get your brain fully developed, you gotta know. See, the thing about maths at this level is you're gonna see the things from a bunch of different ways, and you gotta reconcile them all. And that way, that's what makes you a much better mathematician. Okay? So what we get for A?
40.
40 what?
40.
Degrees. Are we good with that? Simple enough. How about B? 59, you said? Okay, good, easy enough. Talk about C here. Somebody tell me what they don't get for C.
58 degrees.
58? So what'd you do? How'd you do it?
180 minus 50.
So you did 180 minus 90 minus 32, right? Let me ask you this, just as a quick little shortcut for right triangles. They add up to 180, yes? There's 90 of the 180, isn't it? Okay? So if that's 90 of the 180, what's left for the other two angles? The other 90, right? So couldn't we just do measure of angle A equals 90 minus 32? Could we do that? We get the same answer?
Yeah.
What was it?
58.
58 degrees, okay? You get that? You got one angle's a right angle, you gotta have 90 left for the other ones. Now in D, I do want an equation, okay? With x's in it. What would that equation be here? Yes, but I do want you to do that as an equation, and you'll see that we're going to effectively be doing the same thing. What would the equation be, though? Right? That's your equation. Combine like terms. let's see, 2x plus 50 equals 180. What'd you say? You did 180 minus 50 to start out? I think we're going to subtract 50 from both sides. Isn't that what we're about to do? Right? So we get 2x, 180 minus 50 is what? 130. Then what'd you say you did? Hey, what are we about to do algebraically? Divide both sides by 2. Okay? So we get x equals what? 65 degrees. Okay? Everybody with me on that? Not too tough. But know how to think of it algebraically as well as, mechanically. A lot of you do, okay? All right. On the next page. So an isosceles triangle. Hopefully you guys know that isosceles triangles have 2 congruent sides, yes? Well, technically, an isosceles triangle has, the definition has at least 2 congruent sides. An isosceles triangle could have 3 congruent sides, right? So would that, would an equilateral triangle fit the definition of isosceles? Yeah, because if it has 3 congruent sides, equilateral, does that fit with at least 2?
Yeah.
So an equilateral triangle is also isosceles, isn't it? Okay. But anyway, let's just say we got 2 congruent sides of an isosceles triangle. What do you know about the base angles? If these two, if these are the 2 congruent sides, these are the base angles down here. What can you tell me about those base angles? They're congruent, right? Okay. Which means also, if you get a triangle and you see 2 angles are congruent, you know that those opposite sides then are congruent, and it's isosceles. Does that make sense? Okay. So they want us to prove with another transformation that these base angles A and C are congruent. Okay. Isosceles triangle base AC. So I want you to take a minute, read that over, and think about what transformation will happen, and ask yourself, does this kind of look a little bit familiar? I want to be able to connect it to 2 things that we've already done. Okay, so take a minute and read it over. Well, right after that, what's the first? They construct an auxiliary, like the parallel one we did before, but this time it's what? It's the what? Oh. You guys ever construct with a compass a perpendicular bisector?
No. Yeah, line.
And did you also, after you learn how to construct a perpendicular bisector, construct a line of reflection with that very same construction? Yeah. Well, in context they're different, right? But effectively, yeah, right? It depends on what you're talking about. It's sometimes more helpful to talk about it as one and not the other in certain contexts. Okay? So they constructed a perpendicular bisector. Well, that would mean that we got 2 right angles there, don't we? And aren't these congruent? So what's the transformation they're using here to prove that the base angles are congruent? Rotation, reflection, transformation. All right, reflection. So don't forget, reflections are isometric. Okay? Which means that when we reflect at that triangle over the line, it's congruent to itself, right? And what do you know about all its corresponding parts? They're congruent to one another, right? So what's happening here? If they reflect over this line, C will correspond with what? Angle A after the reflection, making C and A what? Congruent. Congruent, because it's an isometric transformation. You see the connection there? So we use the thing we just learned. What did I just lost my train of thought? Oh God, don't ever get 50 years old, kids. Okay.
Tell us to die before them.
Huh?
You're 40.
Oh yeah.
Lordy.
I turned 50 a couple months ago.
Really?
Oh yeah. Yeah. I started drooling, in fact. I'll be in a wheelchair soon. So reflex corresponding parts map, and you map by a rigid transformation, corresponding parts are congruent, and C maps onto A, right? So that proves that the base angles of the triangle are congruent. It also shows that when you construct a perpendicular bisector, you're constructing a line of reflection, right? But then also, who remembers, I think it was yesterday, about points that lie on the perpendicular bisectors? How far are they from the endpoints of this line I got
The
bisected?
same distance.
They're all equidistant from the endpoints, right? And so we've got these two congruent angles, right? And if we think of this now in another context that's just the perpendicular bisector, not necessarily a reflection, right? We know every point on here is equidistant from these endpoints. So what about point B? Is it equidistant from A and C? Which makes segments AB and BC what? Huh? Congruent. So then if you have two angles of a triangle congruent, you could go through this thing here, knowing that points on a perpendicular bisector are equidistant, and say, yeah, those sides are congruent. If those angles are congruent, it's got to be isosceles. All right? We're connecting everything here, aren't we? Okay? All right, let's move down here to a more classic proof. Kind we know and love. So we're given what kind of triangle? Isosceles, which means we know that these two legs are congruent, and the base of it is AC. They want us to prove that angle A is congruent to angle C. In other words, they want us to prove that the base angles of an isosceles triangle are congruent. Let's see what they do, okay? So, given, right? Isosceles triangle, base AC. Now what did they do next?
Draw the line.
Yep, so they constructed that auxiliary line, which is the perpendicular bisector of AC, didn't they, right? So that means we've got right angles, congruent, congruent, because we know what perpendicular bisectors do, okay? And now they state that, don't they? They say that AC is now congruent to AD. What's the reason?
I got this bisector.
Okay, so remember, when you have a perpendicular bisector, you have two things, right? You have a perpendicular line, and you have a segment bisector, right? Which goes through what point, by the way? Segment bisector goes through what point? Midpoint. Midpoint, right? So you remember in a proof, if you're given something as a midpoint, you can say the two segments are congruent. That's kind of what they do. Now, the perpendicular part gives us what?
90 degree, 290 degree angles.
Yeah, so angle ADB, right? That one and that one are right angles. So what are they setting up here? Looks like they're trying to get what? Those angles to be what?
Right.
Yes, right? So after we've established their right angles by definition of perpendicular, what can we now say about these two angles right here? They're congruent. Why?
Already.
Yeah. Hey, could we combine these two statements into one step?
Yeah.
What would it be?
The ABB congruent to angle CBD
And what would be the reason?
because they're right angles.
Perpendicular
Perpendicular, yeah, perpendicular lines. Yeah, you're on the right track. Form congruent right angles.
But I thought you had to state.
Yeah.
Right there it is.
Would you have to specify if they're congruent if you say the right angles? 'Cause-
Well, if you are trying to prove triangles congruent, right, you got to get using angles congruent. So yeah, you have to state that, right? But do you see I included right angles, right? Is that one statement gets it off? See what I mean? That's the shortcut. Okay? So now, we've got a couple of segments here congruent, and we've got these congruent angles here. It looks like they're going after some other congruent side. What would that be? That line they drew. The auxiliary line there, BD, isn't it congruent to itself by the reflexive property? And so now, these two triangles are congruent by what? Huh? Right, everybody with me? Side angle side. Now that they're congruent, can we say that? We've got the triangles congruent, so now why can we say, ultimately, finally here, that angle A is congruent to angle C? CPCTC. We got the triangles congruent. Now we can use CPCTC. Everybody with me on that? Okay, so there's a bunch of different ways to look at proving things, and after you prove them, then officially you can go on and use that fact, for something more practical. Okay, so let's do that now. Here's an example. So we have, what kind of triangle is this? Even if they don't tell you. It's marked with two congruent sides, so it's isosceles, right? So you know these two sides are congruent. What can you now say about these two angles? They have to be congruent, because we've just proven it. We just proven it. We have an isosceles triangle. Those angles are congruent. We did, didn't we? Okay? So they do this, in a practically kind of figured out way. Can we do it algebraically? If that's x and they're equal, right? What's the equation?
X. Well, no. 180.
Right? X plus x is 2x, right? Huh? Subtract, right? So we get 2x equals what? 126. What does x equal? Okay. So we did the same thing here, but algebraically we did over here, really, right? Okay.
Can we do it either way?
Depends. It depends on what you're asked and what I got to move on in that day. I want you to know how to do them both, okay? I really want you to know, like some of these calculations you just kind of do, like in your head. I really want you to know how to make them in an algebraic form, okay? All right. Let's, getting long. Let's take a minute. And actually, I do want you to do A and C algebraically, okay? Set A and C up algebraically and solve for whichever one they're asking for, okay? How about in B? What do we got?
180
So you did 180 minus 78, right? And what's this? 78 minus another 78, and what'd you get? Say it clearly.
102.
Okay, I didn't want to write the wrong number again. Everybody go with that? 102?
Wait, I thought you said just do C. And then.
No.
No, I said I wanted you to do A and D algebraically.
Oh, A and D.
Algebraically.
I heard C.
I heard C.
I heard C. Actually, I heard T, but everyone else heard C, so I just.
Can we change C?
Don't do that, man.
You're recording up.
Have some confidence to act on what you know you heard. Okay? Don't follow it. Don't follow these sheep.
Can we change it to C since most of us said that?
You gotta listen better.
Well, this can't be too hard. What's the measure of angle C?
7.5.
In here?
Yeah.
What now? Yes, ma'am.
For B, I got 24.
Why don't you speak up, guys?
Yeah. Oh, yeah, we weren't finished on that one. We were done.
Where did you get the 102 from?
Well, that's the next answer, and then you do 100.
Come on. No, just, jeez. What's the measure of angle? Just do that. What do you got? What?
I got 51.
24.
Oh my God. I got 51.
It's 24.
It's 24.
Oh, you boy. Okay, over here. What's the measure of angle C?
57.5.
65.
65. It's isosceles. The base angles are congruent.
I'm confused.
Oh, my
How
fault.
did you get 24?
Because 78.
180 minus 78 minus 78.
78, but 78 equals the
You know
number
what?
24.
Okay, but no. 180 minus 78 is 102. 102 divided by 2 is 50.
Why are you dividing by 2?
I don't know.
Yeah, exactly.
Just subtract the other 78.
What did you get to divide?
She's conflated. She's mixing up with the.
Yeah.
Okay.
All right. So algebraically here, I think I'm going to call this isosceles triangle. Maybe call that x and x. So did you have something like this? Right? So 2x equals what, 144? Right? So what does x equal?
72.
72.
Now, check this.
Yeah, I'm gonna, sh-
I got one
it's
thing.
72.
One thing, actually two things.
Okay, now we gotta get to the other triangle. We gotta get to angle D, don't we? What is this other triangle? What kind of triangle? No. It's all, look, it's also isosceles, isn't it?
Yeah.
Which means these guys are congruent, right here, right? So let's get the measure of angle C. How are we gonna do that? Measure of angle C. What are these two? What are these two angles add up to? 180 minus 72, which is what?
108.
108.
Couldn't you just add 36 and 72?
You could, yeah. And that's the exterior angle theorem that we're going to learn later, by the way. You just hit on a theorem we're going to learn later, and you worked out the proof for that theorem very quickly. All right, so now I don't want to use x again, so I'm going to call this y and y. What's the equation? I call these angles y and y. Give me the equation. Plus 108 equals 180. What does 2y equal? Let's see, 180 minus 100
72.
is 80, minus another 8 is 72. What's y equal? 36 degrees. There we go. Okay?